Hello everyone, welcome to this course on special theory of relativity. First of all, special theory of relativity is a beautiful theory on nature, and it is beautiful in a sense that it is very, very non-intuitive, and it really goes against our intuition and on our basic assumptions on the nature of space and time. So in that sense, it is a very, very beautiful theory. And before, like around 200 years before the discovery of special relativity, the laws of nature were described by the three laws that were by the three famous laws of motion given by Newton. And for around 200 years, it was thought that they give the correct notion, the correct theory on nature. But then, in the beginning of the 20th century, it was found that the laws of motion given by Newton were actually inconsistent with the observations. And so, to make our theories consistent with the observation, Albert Einstein discovered this theory on special relativity, and it was discovered in 1905. So before going any further, let us first discuss what will be the contents of this course. So in the beginning, we will discuss about pre-relativistic physics. That is the physics before special theory of relativity was discovered. And the idea behind discussing pre-relativistic physics is that we want to know what exactly was the problem in the laws of motion given by Newton, and what exactly was the problem in the notion of space and time before special relativity emerged. So, so we will talk about the first law of motion, and so we'll first talk about the first law of motion, and we will, in discussing about first law of motion, we will talk about inertial and non-inertial frames and what do they mean, and uh, like what is meant by them, and what are its implications. Then we will discuss about the second law of motion, and after that we'll discuss about Galilean transformation. So what does Galilean transformation means? Galilean transformation tells us how, like, if we measure velocity in some frame of reference, for example, if we are standing on the ground and we measure velocity of a particle, then Galilean transformation tells us what would be the velocity of that particle when viewed in a different frame of reference. For example, what will be its velocity when viewed from a bus, which is itself traveling in, like, say with some speed of 20 kilometers per hour. So this is what is told to us by Galilean transformation. Then we will see what happens to the Newton's laws under a Galilean transformation. So what happens to these first law and second law of motion when we go from one frame of reference to the other? So what happens to them when we go from ground to a bus traveling by 20 kilometers per hour? And after discussing all of these things, we will find that we will first discuss what do they tell us about the speed of light. So what does Galilean transformation tell us about the speed of light in different frame of references? And there were some experiments conducted in the beginning of the 20th century, and also we will also see that there were some inconsistencies of these laws of motion with the Maxwell's equations. And because of these inconsistencies, we had to throw away the pre-relativistic physics, and because of this reason, the relativistic physics was discovered. So after this, after completing and seeing what is wrong in the pre-relativistic physics, we will first talk about the postulates of the special theory of relativity. So, a postulate is something that we assume to be correct, that we take as a given because these are consistent with our observations. So, the way we know about nature is through observations. So, we need to assume some things based on these observations, and these assumptions are called postulates. So we will discuss about in the second part. We'll discuss about these postulates of special theory of relativity. Then, in the third part, we will be talking about the kinematics in special theory of relativity. So we saw how we will see in the first part that how do velocities and accelerations transform when we go from one frame of reference to the other frame in the pre-relativistic physics. So after throwing away the pre-relativistic physics and establishing the postulates of special theory of relativity, we need to know how do these velocities and accelerations change in this if we assume the postulates of special theory of relativity. So this will be contained in the kinematics of special theory of relativity. And in this, we will be talking about some very fascinating things such as length contraction, time dilation, and simultaneity. And all these things will be really, really anti-intuitive in some sense because we do not encounter these things in our daily life. And these effects, we will see that these effects become noticeable only when one goes near the speed of light. So after this, we will talk about Lorentz transformation. So Lorentz transformation tells us, captures all of these things about length contraction, time dilation into set of some very simple equations. After this, we'll talk about how do velocities transform in the special theory of relativity. And in the last part of the kinematics, we will talk about the third postulate of relativity and causality. So causality means causality is a very intuitive idea. We know that things really follow chronological order. So we know that for something to happen, for an effect to happen, it must have a cause. And this cause and effect relationship is captured very beautifully by causality. And we will see that if we do not uh, talk about the third postulate of relativity, if we do not give importance to the third postulate of relativity, then causality really breaks down in the sense that effects can precede cause, and someone can kill his own mother before his birth and things like that, which are not acceptable from a very very intuitive sense. And in the last part, we will be talking about the dynamics of special relativity. So in dynamics, we know that in pre-relativistic physics, the dynamics are captured by the second law of motion. So the second law of motion, which is F equals ma, tells us that how should a particle move if a force is applied on it. So after throwing away the pre-relativistic physics, we want to know about how this F equals ma changes and what is the F equals ma version in special relativity. So that will be captured in the dynamics of special relativity. And here we will talk about relativistic momentum and mass, relativistic energy, and the famous formula E equals mc squared. We will talk about kinetic energy in special relativity. And after this, we will see how does the second law, we will finally write down the second law of motion version, the special relativistic version of second law of motion. So that is about the contents of this course. So without wasting any time, let us get started. So the topic of this video is pre-relativistic physics. So we want to learn what actually went wrong. Why did we have to introduce this theory of special relativity? So let us talk about some very basic concepts of the pre-relativistic physics. So first, let us talk about the Newton's first law. What does Newton's first law say? The Newton's first law says that an object at rest or in a uniform motion maintains its state until an external force is applied. So what does this mean? This means that if an object is not moving at all and it is at rest, and if nothing external is going to disturb it, then it will remain at rest. And if that object is moving with a uniform velocity, that is a constant speed in a same direction, that is a constant speed in a straight line, then until and unless an external force is applied on it, it will keep on moving. It will keep on moving in that state. Now, let us view this statement that all of you must be knowing already in a slightly different way. So let us say that we have an object over here which is moving in this direction with a speed v. So and there is no external force. Let us say that we have isolated this particle from the rest of the universe. So the first law says that this object must continue moving with the same speed in the same direction. But it is we are not talking about in what frame are we measuring this speed of the particle. So I can say that there is an observer S which itself is accelerating in this direction relative to this particle. So this frame of reference, because this frame of reference is itself accelerating with an acceleration a, then a person standing inside this frame must notice that this particle, which let us call a, is accelerating in the opposite direction. That is, it is accelerating towards right without any force acting on it. So this person will say that the object is not moving with constant speed even when it is isolated. So this person would come to us and say that Newton's first law is actually wrong because I just saw a particle which was isolated from rest of the universe, and that particle was accelerating with an acceleration a. So there is something incomplete about this statement that we have just made. So let us complete this statement. What first law actually says is that there exists some frame of references that we can call inertial frames, in these special frames called inertial frames. So what this law says is that if we are in these special frames, only then we will see that an object at rest remains at rest and an object in uniform motion maintains its uniform motion. So in other words, the Newton's first law says that these special inertial frames exist. This is what the Newton's first law really means. So, so here we can say that there exists some frame in which an object remains at rest or remains in a state of constant velocity. And right here we can define what we mean by non-inertial frames. So as the name suggests, non-inertial frame is a frame which is not inertial. So it is that frame in which Newton's first law is not valid, or in other words, it is that frame in which an object is under acceleration even if it is isolated by the rest of the universe. So this is what we mean by an inertial frame of reference and a non-inertial frame of reference. Okay, very good. Let us move further now. So moving forward, let us now discuss about the second law of motion. So in the first law, we saw that if we are in an inertial frame of reference, then if the object is isolated, then it remains at rest or remains in a constant motion. But what happens to a particle if it interacts with other particles? What happens to that particle if something exerts a force on that? So this is stated by the second law of motion. The motion states that when a force F is applied to a particle of mass m, then it accelerates with an acceleration which is equal to F by m. So if I exert a force F on a particle which has a mass m, then it will accelerate. That is, its velocity will change with a rate that is equal to F by m. Okay. So this is what the second law of motion states. Now, having discussed about the two laws of motion, let us now look at the Galilean transformation. So what does a Galilean transformation mean? Let us say that we are in a particular frame of reference. So let us say that we are standing on a ground, and on the ground, I draw some Cartesian coordinates. So this direction I'll call X, and I have a direction Y. And I don't know why it is not working. Okay. So I'll call this direction. I'll call this direction X, and I'll call this direction Y. So yeah, and this direction Z. Let us call this frame S. So this particular frame is called S. And let us say that there is a particle at this point, which is given by the coordinates X, Y, and Z. And we have a clock in this frame which shows a time t. So we can say that this object A is at a point x, y, z at a time t. Now we want to know about the position of this particle in a different frame of reference. So let us say that we are in a different frame of reference in which the coordinates are marked by x prime, y prime, and z prime. And this frame of reference, which is S prime, is moving with respect to the frame S in the positive x direction with a speed v. Okay, so now we want to know about the and another thing is that this frame of reference coincides with the frame of reference S at time t equals 0. Okay, so this is important. So what happens to what is the position of this particle at of this particle A in this frame of reference S? Clearly, the position, because the frame S prime is moving with a speed v in the positive x direction. So let me draw another diagram. Let this be the origin O. Then at time t, we know that the origin of S prime would have moved a distance vt. All right. So the x coordinate of this particle A would be measured to be x minus vt in the frame S prime, because S prime has itself moved by a distance vt. Hence, x prime is equal to x minus vt. And since the frame S is not moving in either y or z direction, we can say that y prime is equal to y, z prime is equal to z. And now comes a very important point. Before special relativity, it was thought that there exists a universal clock, or in the other words, it was assumed that there is a clock which runs at the same rate for all the frames of references. So if the clock of S is showing time t, then the clock of S prime must also show a time t, because we know that both of them were showing a time t equals 0 when their origins were on top of each other. So these four equations give us the Galilean transformation. So these four equations tell us how does the position of a particle change when we change the frame of reference. This is called this is called Galilean transformation. Now let us move forward. Yeah. So now we want to see how do Newton's laws, in particular, how does Newton's second law change when we change the frame of reference. So let us do it. Let us say that we have a particle A which is at a position x, y, and z at time t, and let us say that it is accelerating with an acceleration a in S frame. Now, from Newton's second law, we know that F should be equal to ma. All right. So now let us see whether this statement F equals ma remains true if we go into another frame which is moving at a constant speed with respect to the frame S. So let us go on to our frame S prime that was introduced earlier. In this frame S prime, the position of the particle is given by x prime, y prime, and z prime, and time is given by t prime. But because t prime is equal to t, I am just going to write it as t. So what is the acceleration a prime of this particle A in this frame? In this frame, a prime is equal to dx prime over dt I cap plus dy prime over dt j cap plus dz prime over dt k cap. Okay. Now let us substitute the value of x prime from this equation. So from that equation, we know that x prime is equal to x minus ct. Oh, I've made a mistake over here. This should not be acceleration. This is actually velocity v time in this frame. So in this frame, let us call the velocity u prime. So in this frame, the velocity of the particle is going to be equal to it is going to be equal to dx over dt minus d over dt of vt I cap plus dy by dt j cap plus dz by dt k cap, which is equal to u, which is the velocity of the particle in S frame, minus v in the I cap direction. Okay, and now it is very clear that if we want to obtain the acceleration a prime, we have to differentiate this quantity once again. And because v is constant, so its derivative with respect to time will be 0, and hence a prime will be equal to du over dt, which is equal to a itself. So in other words, the acceleration of the particle remains same in the frame S and S prime. And therefore, we can say, let me write this thing clearly. So we can say that acceleration in the S prime frame is same as the acceleration in the S frame. So in other words, the Newton's second law remains invariant, or in the other words, Newton's second law remains same in both frames S and S prime. So we can say from this calculation that the laws of motion are same in all inertial frames. Or in other words, we can say that if we have a frame of reference which is moving with a constant velocity with respect to an inertial frame, then that frame of reference is also inertial. All right. So this is what is known as, this statement is called Galilean relativity. All right. So far we have learned that Newton's first law and Newton's second law remain invariant when we go from one inertial frame to another frame which is moving with a constant velocity with respect to the first inertial frame. And based on this, we are saying that any frame of reference which is moving with a constant velocity relative to an inertial frame is also an inertial frame. All right. So far, so good. So where did the problem actually come? So from the Maxwell's equations, from the theory of electrodynamics, it was shown by Maxwell that the speed at which the electromagnetic waves travel is given by 1 over under root mu naught times epsilon naught. So what does this mean? I'm sorry for the interruption. Yeah. So what does this mean? Am I audible? Yeah. Sorry for the interruption. So what does this mean? This means that because it was known in the Maxwell's equation that the value of mu naught and epsilon naught does not change as we go from one inertial frame to the other frame. So this should mean that the speed of light should also remain same as we go from one inertial frame to the other. But this is not quite consistent with the pre-relativistic physics. How? Let us see. Let us say that we are in our good old frame, S frame, in which someone enlightens a torch and we have a light wave traveling from this point. So we know that the speed of light would be c. Now consider another frame, our good old frame S prime, which is moving with a velocity v in the x direction with respect to frame S. Then in this frame S prime, we must see that the velocity of light is not c but c minus b. So we see that we see by Galilean relativity, by the Galilean transformation, that the speed of light should change as we go from one inertial frame to the other. But by Maxwell's equation, we see that the speed of light must remain same. So we see that there is an inconsistency between the Maxwell's equation and the Galilean transformation. So one of these things must be wrong. Either Maxwell's equations are wrong or the Galilean relativity is wrong. So, so when we come to a point of an inconsistency between two very fundamental theories of nature, then the only way to resolve it is through experiments. So in the late 19th century, if I am not wrong, there was an experiment conducted by Michelson and Morley, and that experiment actually showed, sorry again, so I'm sorry for the interruption. So, so that experiment by Michelson and Morley actually showed that Maxwell's equations are right and the Galilean transformation is the thing that is actually wrong. So these showed us that the postulate that I'm sorry, these things showed us that Galilean transformation must actually be wrong, because in this experiment it was showed that speed of light is same in all directions and is not affected by the Earth's motion at all. So this was the very important point and a very surprising point and a very surprising point at the same time to everybody, because Galilean transformation is a very intuitive idea. If you think intuitively, then if a light beam is moving with a speed c in some frame, it must move with the speed c minus v in another frame. It is really very intuitive. So what can be wrong in in these equations, which are called Galilean transformation, and why exactly, where exactly does this fail when it comes to speed of light? So these things will be discussed in the next video, in which we will start with the postulate of special relativity, the starting points of our theory, which are the statements which we assume to be correct based on experiments. And from there on, we will see what exactly is wrong in Galilean transformation and what should we use in place of Galilean transformation. And the answer is Lorentz transformation, as we will see as we go along in this course. Thank you very much for watching this video. And I will keep posting these videos once every week. So see you in the next video. Thank you very much.